Welcome to our second lesson. In our previous lesson, we looked at moments and we defined what moments is, and we found that actually a force causes a turning effect. We went ahead and looked at the factors that affect moments, and we found it is simply the magnitude of the force that is causing the turning, and also the perpendicular distance from where we have the turning point to where the line of action of the force is. And we went ahead also and found that to calculate for moment, it is found by multiplying the force and the perpendicular distance. We are going to look at two examples on the same, on calculation of moment. Look at such a system where we have a bar and we have a turning point, that is the position of our pivot, and this is our force. It is a force of 5 newtons. Remember, we represent force with a straight line and an arrow to show the direction of the force. I would like you to note, as we do this example, there is one thing we are assuming. We are assuming that this bar is weightless, that this bar has no weight. In another lesson, we are going now to look at a situation where we bring the effect of the weight of the bar into consideration. So this is a force of 5 newtons, and we said when we have the force acting along, then the line of action of the force is acting along that line. This is the turning point, and therefore the perpendicular distance from the pivot to the line of action of the force is 20 centimeters. Now, how do we calculate for the moment caused by this force of 5 newtons? Then moment is force times distance. Our force is 5 newtons. Our perpendicular distance is 20 centimeters. Again, you need to recall that anytime now we incorporate a measurement in any calculation, then that measurement should be in its SI units. And the SI units of length is meter. Therefore, we divide 20 centimeters with 100 so that it gives us 0.2 meters. Multiply that with our 5 newtons and we get 1.0. Very important. Every physics answer which has a quantity that carries SI units, we must always include the SI units to that value. And therefore, the moment caused by these 5 newtons will be 1.0 Newton meter. On to our second example here. Look at the position of our pivot. This is our force, a force of 3 newtons. This force is acting on the bar at an angle. Therefore, it's not perpendicular to this bar. And the angle at which the force is acting on this bar is at an acute angle of 30 degrees. Then in this case again, still our moment will be, and you can see that this is not supposed to be momentum, that's supposed to be moment. Our moment should be force times distance. Our force is 3 newtons. Our distance is 5 meters. This is the distance from the pivot to the point at which the force is acting. But is this the perpendicular distance? No, because this distance is meeting the line of action at an angle of 30 degrees. Therefore, we must go ahead and get the distance from the turning point, the perpendicular distance from the turning point to the line of action of this force. And when we have that, then we create a right-angled triangle. And at this point now, our moment being force times distance, we already have the force, it's 3 newtons. We need now to calculate for that perpendicular distance, D. How do we get it? This being a right angle triangle, we can use trigonometric ratios. 30 degrees, D will be the opposite of 30 degrees. Our 5 meters is our hypotenuse. Therefore, the sine of 30 degrees will be the opposite, which is D, divided by the hypotenuse, which is 5 meters, as shown there. And therefore, we can get the value of our D as 5 times the sine of 30, which will give us 2.5 meters. Note that our 5 was already in meters, no conversion required. And therefore, our moment caused by the 3 newtons will be 3 times 2.5, which is 7.5. And again, the units, Newton meter. So you can see now, simply, to calculate for moments, it is force times the perpendicular distance. This case, we took it direct. This is the perpendicular distance. This case, we could not take this distance. It is not the perpendicular distance. In the next part, we'll be looking at the principle of moments. So we want to look at principle of moments. And for us to understand the principle of moments, there are a few things that we need to understand or get very well. With me here is a meter rule. I want to lift it up so that it won't look like it is connected to my pivot here. This is my pivot. It is a knife edge. I have a meter rule. I have two masses. This is a 100-gram mass and this is a 50-gram mass. When I place, and remember I said that in this case we have a bar here, but for me to remove the effect of the weight of this bar, I'm placing the pivot at the central mark, at the 50 centimeter mark. And you can see that there is some slight of balancing, and if I was to remove this mass, you can see the bar will tilt to that side. So for us to understand the principle of moment, this force here is making this bar to turn like that. This is the same rotation that is taken but by the hour clock or the minute clock of definitely the clock, and we call it a clockwise direction. If you are to remove that mass and place this one, then again this turns in this direction. The system turns in the opposite direction. Now this is anti-clockwise. So this force here is making the system to go in a clockwise direction, and this one here is making the system to go in an anti-clockwise direction. Therefore, we have what we call clockwise movement and anti-clockwise movements. And how do we identify them? We just check where are the forces making the system to turn. When the force acts on that system, is it going in a clockwise direction or is it going in an anti-clockwise direction? Therefore, in this case, my 100-gram mass here is causing a clockwise movement, and my 50-gram mass here is causing an anti-clockwise moment. So I have two moments here. One is anti-clockwise, the second one is clockwise. Now, I can make sure that this system balances. You can see at this point, this is falling to this side. So I reduce the distance. the system is balanced. The moment the turning effect cost here is equal to the turning effect cost here. So the system will not turn anywhere because the moment trying to turn it to the clockwise side equals to the moment making it to turn to the anti-clockwise is equal to the clockwise. In that case, we say that that system is in equilibrium. The system is at equilibrium. And why or when do we have the system at equilibrium? It is when it can't move or it can turn to either the clockwise or anti-clockwise because the two are equal. And it's at this point that we get our principle of moments. The principle simply is about a system which is at equilibrium. And it is simply that this clockwise movement will be equal to the anti-clockwise movement when the system is at equilibrium. We can actually add another force there to cause a second movement. You can see now the anti-clockwise is increasing. So what do? I simply increase the perpendicular distance. And I can also reduce the distance on the other side. There we are. On this side, I have two anti-clockwise movements, but still on the other side, we have one clockwise movement. These are two. They have balanced with the other one. Again, when we take this movement, we add to this movement, it will be equal to the movement on the other side. And that is why when we are stating the principle of moments, we emphasize that it doesn't have to be one moment. It doesn't have to be two. We could even have 5 forces here. But when we add all those moments together, as long as this system is in equilibrium, they'll be equal to the moment on the other side. And that brings us to the principle of moments, which simply states that for a system in equilibrium, the sum of clockwise moments equals to the sum of anti-clockwise moments about the same point. For a system in equilibrium, the sum of anti-clockwise moments equals to the sum of clockwise moments for a system at equilibrium. Key points to note in that particular principle that it is for a system in equilibrium. 2, it is the sum of all the clockwise moments that is equal to the sum of all the anti-clockwise moments. And all these moments are acting about the same point. And here we have 2 diagrams which will be looking at how do I identify which is clockwise, which is anti-clockwise. This force F1, where will it turn our system? In that direction. When I'm considering this force, I completely forget about the other. So it will turn it this way. So in this case, F1 will be anti-clockwise. F2, it is turning this system. This system will turn like this, clockwise movement. By the look of things, which forces here are clockwise and which one are anti-clockwise? Let's look at F1. I only need to check where is the pivot. This is the pivot. F1, clockwise, anti-clockwise. Which direction will the system turn? that will be clockwise. F2, it will also be clockwise. This will turn the system this way. This will also turn the system in that direction. Therefore, this will be anticlockwise. This is anticlockwise, so anticlockwise, anticlockwise, clockwise, clockwise. Thank you. We'll now be looking at 1 or 2 examples on calculation on principle of moments. Thank you.